Hello everyone, this is Koduru Chandrasekhar and today I'm going to present about the topic efficiency and voltage regulation of a transformer. These are the topics which we are going to cover in this presentation. Coming to the equivalent circuit of the transformer, we have I1 and I2 which are the primary and secondary currents, R1 and R2 which are the primary and secondary resistances, X1 and X2 which are the primary and secondary leakage reactances, V1 and V2 which are the primary and secondary terminal voltages, and E1 and E2 which are the primary and secondary induced EMFs. So coming to the efficiency of a transformer, efficiency of a transformer is defined as a ratio of the output to input power. So efficiency is denoted by a symbol eta, which is equal to output power divided by input power into 100, 100 for the percentage. Input power can be written as input power equal to output power plus losses. Input power equal to output power plus copper loss plus iron loss. Losses in transformer can be mainly categorized into two types: iron losses and copper losses. So iron losses, we have hysteresis losses and eddy current losses. So by rearranging the formula, we get percentage efficiency is equals to output power divided by output power plus copper losses plus iron losses. So as the transformer does not contain any rotating parts, there are no rotational or frictional losses. Therefore, the efficiency of transformer is quite high, and if well designed, the transformer efficiency may be as high as 99%. So the formula for calculating the efficiency of the transformer, eta is equals to output power divided by output power plus iron losses plus copper losses, which is equal to V2I2 cos phi 2 divided by V2I2 cos phi 2 plus iron losses plus copper losses. So Pi and Pc are iron losses and copper losses respectively. V2 is the secondary terminal voltage, I2 is the secondary current, cos phi 2 is the power factor of the load. So if the transformer has been operated at any other fractional load, so we introduce another parameter x, which is equal to the actual load divided by full load. So x is equals to I2 divided by I2 in full load. So I2 is equals to x times of I2 at full load. Okay. So if x is the fraction of the full load, the efficiency of the transformer can be written given by the relation eta x is equals to x into V2 I2 cos phi 2 divided by x into V2 I2 cos phi 2 plus iron losses plus x square into I2 square into R2 ES, which is the copper losses. Okay, so the copper losses vary as the square of the fraction of the load. So at the end, the important formulas that we have to remember is the percentage efficiency is equals to x into V2 I2 at full load into cos phi 2 divided by x into V2 I2 at full load into cos phi 2 plus iron losses plus x square into I2 square in I2 square into FL into R2 into E into 100. So I2 square into FL into R2E is the copper losses. Okay. So we can also write efficiency as x into VA rating of the transformer into power factor divided by x into VA rating of the transformer into power factor plus iron losses plus x square into copper losses at full load. So coming to the condition for the maximum efficiency of a transformer, for in any function, if we have to find maximum and minimum of a function, we have to generally differentiate it and equate to zero, and we have to find the points of extremum. So in case of efficiency also, we'll differentiate it with respect to I2, as I2 is the variable here, rest all other parameters are constant. So when we differentiate it with respect to I2, we use U by V rule. So the denominator is greater than 0, so we'll work out with the numerator only. So when we rearrange the terms in the numerator and we simplify, we get the iron losses minus I2 square into R2E, which is the copper losses, which is equal to 0. So we'll get the copper losses are equal to the iron losses, which is the condition for the maximum efficiency. We can also say that the variable losses are equal to the constant losses here. The formulas derived by the condition of maximum efficiency are efficiency eta maximum is equals to P2 I2 cos phi 2 divided by V2 I2 cos phi 2 plus 2 Pi, since Pi is equals to Pc. So the value of the output current I2 at which the efficiency of the transformer will be maximum is given by I2 is equals to under root of iron losses divided by secondary resistance R2Es or RES. Okay, another important formula which is to be noted here is that the value of X at maximum efficiency is under root of iron losses divided by copper losses. So why efficiency of a transformer is important? The core losses depend on the transformer rated voltage and the copper losses depend on the currents to the transformer. Hence, transformer efficiency is of prime importance to operate it under constant voltage and frequency conditions. Okay, so coming to the graph of power loss and efficiency versus percentage load, we can see the graph of efficiency and the at the in the blue one. So the maximum efficiency is obtained here and the load at maximum efficiency is here. So the core loss, as you can see, is constant, and the copper loss is not constant here. It is varying according to a function. So coming to the graph of efficiency versus load current, the variation of efficiency with loading can be represented by the figure below. So at unity power factor, we'll have maximum load and rest all will have a efficiency less than the maximum efficiency. So the maximum efficiency occurs at unity power factor, and the maximum efficiency occurs at same loading irrespective of the power factor of the load. So the maximum efficiency does not depend on the loading, but it depends on the power factor. So coming to the all-day efficiency of a transformer, it is an energy-based efficiency calculated for distribution transformers. A distribution transformer loading continuously fluctuates for 24 hours a day. As core losses are independent of load, the all-day efficiency depends on the copper losses. High energy efficiencies are achieved by restricting core flux densities to lower values, as the core losses are dependent on flux density, achieved using relatively larger cross-section or larger iron to copper weight ratio. All day efficiency eta all day is equals to output in kilowatt hour divided by input in kilowatt hour power. Introduction to voltage regulation of a transformer. So coming to voltage regulation of a transformer, we have two cases here. So in the first case, we have a load attached in the secondary side of the transformer. In the second case, we do not have a load attached to the secondary side of the transformer. So in the first case, we cannot say that E2 is equals to V2 as there is a load attached. But in the second case, we can say that E2 is equals to V2 as it is in an ideal condition as there is no load attached to it. This is a major difference which we need to remember. So coming to the voltage regulation of a transformer, it is defined as the change in magnitude of the secondary voltage of the transformer when the load changes from full load to no load condition, assuming the primary voltage to be constant. It defines the ability of a transformer to provide constant voltage at variable loads. So percentage voltage regulation is equals to change in output voltage divided by no load output voltage into 100. So percentage voltage regulation is equals to no load output voltage minus full load output voltage divided by rated voltage into 100. So coming to the simplified circuit of a transformer, in when referred to the secondary side, we at ideal condition we have E2 is equals to V2. Okay, but at load condition we cannot say that E2 is equals to V2. In fact, V2 is less than E2 in this case. So if we consider a current I2 flowing in the secondary side, we can apply Kirchhoff law and we can say that V2 is equals to E2 minus I2 into R02 minus I2 into X02, or V2 is equals to E2 minus I2 into R02 plus J times of X02, which is a notation of representing it. So R02 X0 plus J into X02, the inside the bracket, it is basically referring to the impedance on the referring to the secondary side. So V2 is equals to E2 minus I2 into Z02. So percentage voltage regulation is equals to E2 minus V2 divided by E2 into 100. So that this is the formula which we have to remember, where percentage voltage regulation is equals to E2 minus V2 divided by E2 into 100. So coming to the derivation of the voltage regulation, formula for the voltage regulation, first we'll draw an horizontal line V2, which is taken as a reference. So if we are assuming an inductive load here, so the voltage always leads the current. So I2 will be drawn I2 will be drawn below the V2. So I2 will be drawn below the V2 and the phase angle here is phi. So I2 into R02 is in the same phase as I2. So it will be drawn parallel to I2 here, which is in the green line. So, and I2 into X02 will be perpendicular to I2 into R02, which is the line FDF. Okay. So E2 will be the line OF here, if we see. So after naming all this, we have to make a construction here. So we will draw a perpendicular F to E, F and extend it up to E, and then we'll join D and E. Okay, so we'll get a right angle triangle here. Basically, if we we'll get a right angle triangle here. So we'll apply Pythagoras theorem here. So Pythagoras theorem, according to Pythagoras theorem, OF square is equals to CF square plus OC square. So we need to find the length of OC and CF here to find the value of E2 here. Our main purpose is to find the value of E2 in this case. So the value of OC will be equal to V2 plus I2 into R02 into cos phi plus I2 into X02 into sin phi. We are basically taking components here. So and the value of CF will be equal to I2 into X02 sin phi. here the phase angle at here also I2 into R0 it is same as both are in the same phase here. That's why phi angle, if phi angle is here, phi angle will also be here. Okay, so OS square is equals to CF square plus OC square according to Pythagoras theorem. So E2 will be equal to under root of V2 plus I2 R0 to cos phi plus I2 X0 to sin phi whole square plus I2 X0 to sin phi whole square. For solving this equation, we must know the values of V2, I2, R0 and X0. So we'll basically use an approximation here for finding the value of E2, taking OF and OC negligible. Angle between OF and OC negligible. So here we are taking this phi dash as negligible angle in order to obtain a result. So when we take the angle between OF and OC negligible, we get the value of E2 as approximately equal to V2 plus I2 R0 to cos phi plus I2 X0 to sin phi. So this is E2 for inductive and resistive load, as there is a plus sign here. For capacitive load, E2 is approximately equal to V2 plus I2 R0 to cos phi minus I2 X0 to sin phi. As in the derivation, if we can see in a capacitive load, the value of I2 will lead the voltage. The current will always lead voltage in a capacitive circuit. Okay. That's why we'll get E2 is approximately equal to V2 plus I2 R0 to cos phi minus I2 X0 to sin phi. So in a generalized form, we can write E2 is approximately equal to V2 plus I2 R0 to cos phi plus minus I2 X0 to sin phi. So the percentage voltage regulation here will be E2 minus V2 divided by E2 into 100. Okay, which is the formula here. So if we substitute the value of E2 in this formula, we'll get percentage voltage regulation is equals to I2 R0 to cos phi plus minus I2 X0 to sin phi divided by E2 into 100, which is the important formula which we need to remember this one. Okay, if the load is inductive or resistive, there is a positive sign will come between I2 R0 to cos phi and I2 X0 to sin phi. If the load is capacitive here, we'll get a minus sign in between. This is a generalized formula of the voltage regulation. So if we refer to the primary side, when we derive everything, we'll get the same result. Like but here V1 will be greater than E1 in this case. So V1 will be approximately equal to E1 plus I1 R01 cos phi plus minus I1 R0 X01 sin phi. So percentage voltage regulation will be equal to I1 R01 cos phi plus minus I1 X01 sin phi divided by V1 into 100. So condition for zero voltage regulation. So in case of inductive and resistive load, we have I2 R0 to cos phi 2 is greater than I2 X0 to sin phi 2. Sin phi 2. Okay. So voltage regulation is always positive in case of inductive load. In case of capacitive load, the voltage regulation becomes zero after a certain power factor, and the voltage regulation becomes zero at capacitive load itself. So I2 X0 to sin phi is greater than I2 R0 to cos phi in case of capacitive load. If the voltage regulation becomes zero, we'll have I2 X0 to sin phi is equal to I2 R0 to cos phi. So here we'll get tan phi is equals to R0 to divided by X0 to. So phi is equals to tan inverse of R0 to divided by X0 to. This is the phase angle at which the voltage regulation becomes zero. So the power factor cos phi at which the voltage regulation becomes zero is cos of tan inverse of R0 to divided by X0 to. This is a leading power factor, as a capacitive load will have a leading power factor and inductive load will always have a lagging power factor. So in this case only the E2 is equals to V2, which is an ideal condition. Okay, so the zero voltage regulation of a transformer, zero voltage regulation indicates that there is no difference between its no load voltage and its full load voltage. This means that in the voltage regulation equation above, voltage regulation is equal to zero. Zero voltage regulation is possible only for leading power factor. If the power factor is increased beyond the zero volt regulation condition, then the voltage regulation will become negative. Negative voltage regulation means that the secondary terminal voltage V2 is more than the no load generated EMF E2. Another important thing to note here is about the leakage impedance angle theta, which is equal to phi 2 or phi, which we have already derived here, which is tan phi. Tan phi is equals to tan inverse of R0 to divide by X0. Okay, so that is only leakage. We can also call that as leakage impedance angle as well. So we can say that the maximum voltage regulation occurs when the load power factor is equal to the leakage impedance angle. Okay. Coming to the key takeaway, a transformer's true value lies not just in its power handling, but in its efficiency and stability under varying loads, a balance of performance and precision. These are some of the references. Thank you.